Hello, and thank you for listening to my virtual ICCE 2020 talk entitled Wave Effects on Storm Surge in a Small Two-Inlet Bay. My name is Mara Orescanin, and I'm a professor at the Naval Postgraduate School. I'd like to begin by acknowledging my co-authors from the Army Corps of Engineers and Woods Hole Oceanographic Institution, as well as my student, Lieutenant Commander Matt Reffitt, who really pioneered this research. So to start off with what actually constitutes a small bay, I will direct your attention to the inset, regional inset, showing Boston and Cape Cod, which is the coast of Massachusetts on the east coast of the United States. In the red circle on the southern part of Cape Cod are two islands, one which is Martha's Vineyard on the western side and Nantucket on the eastern side. Where that red circle is centered highlights the zoomed in region, which you can see, which shows Catema Bay. I will draw your attention also to the yellow scale bar, which indicates 1 kilometer. The system, essentially from north to south, spans about 7 kilometers in total. And it's an interesting small little system because it is home to not only one of New England's premier harbors for yachts, which is up in Edgartown, indicated by the red circle, but it also has two inlets, one connecting to Vineyard Sound and a second called Catema Inlet, which connects the Atlantic Ocean to Catema Bay. And Catema Inlet is really home to a very complex set of bathymetry and ephemeral nature. It shifts, it changes, sometimes it's closed, sometimes it's open. But when Catema Inlet is open, waves push water through the system. And because there is this other inlet to the north, there is not a residual wave setup in a small bay as you might expect with a single inlet system. Rather, waves push the water continuing out through Edgartown Channel. It's also further interesting because it is subjected to frequent hurricanes and nor'easters, meaning extreme events are not uncommon. And so just to highlight what I mean by a variable geometry and how this system changes, I'm showing you satellite imagery ranging from 2011 to 2015. The yellow arrow indicated in the 2011 image shows the point at which Catema Inlet breached during a nor'easter in 2007. The white arrows indicated and pointing up indicate the breach and what is also called Catema Inlet to the south, and how it shifts from 2011, where it is roughly north-south oriented. It is rather short, but much wider, on the order of 400 meters wide. And by 2014, it shifts so that it is nearly east-west oriented, much narrower on the order of tens of meters and much longer. Eventually, in April 2015, the system completely closes up. And just for kicks, I thought I'd show the February 2015, where yes, that is in fact frozen water and frozen water levels. And so this brings me to the research question, which is storm surge in small bays possible to accurately model? What are the driving processes that affect surge in these systems? So in order to answer that question, my student did his master's thesis looking at storm surge on much higher resolution scales. And what we knew going into this is that storm surge forecasts often exhibit a consistent low bias, which was partially due to the emission of small-scale systems, such as this system at Catema, as well as insufficient resolution. And what we also knew going into this was that C-storm, which is a coupling of ST wave and AdCirc, both a wave model and a circulation model, has really been shown to adequately model storm surge on much larger, more regional scales. This was very well done and compiled in the North Atlantic Coast Comprehensive Study, which is shortened to NACS. And this coupling essentially means that there's an exchange of information between AdCirc, which is the circulation model, and ST wave, which is the wave model. And that really means that AdCirc is sending elevation and velocities to ST wave, and ST wave in turn sends wave radiation stresses. So this information is passed back and forth every time ST wave has an output, which is on the order of 30 minutes for this system, but that the bathymetry and wind forcing are identical between these models. And this coupling is done using what's called the C-storm model, developed by the Army Corps of Engineers. And so back to Hurricane Irene. Hurricane Irene passed through the system actually as a tropical storm, although it was a hurricane prior to landfall in Long Island. On August 28th, 2011, its closest point was approximately 300 miles to the west, and offshore waves peaked at 14 meters. This is open Atlantic Ocean large-scale waves. Once we got into the nearshore region, the waves off the coast of the southern beach in the Katama system were actually closer to 5 meters during this extreme event. And so why I'm studying and why I'm presenting results from Hurricane Irene was because of a serendipitous field experiment that was going on at the same time, where we had actual observations indicated by the red points. And so we had 5 locations from the north in Edgartown at point 1, all the way to the south at Katama Inlet at point 5. I'm also showing a point 6, which is just off the Ebb Shoal, but it shows this just as a model comparison because we did not have observations at this particular point. And why this is so helpful is that this not only gives me a time series to compare my model to data, but it also gives me some spatial indication as to how well the surge is measured and predicted between the 2 different methods. And so just to bring that back to how we're getting the larger scale dynamics, the NACS AdCirc mesh is much larger, encompassing the entire western North Atlantic, including the Caribbean and Gulf of Mexico. This is a very large, computationally demanding model. And as such, the coastal resolution near Katama was on the order of 200 meters. If my inlet is only 400 meters across, that's a problem in terms of model resolution, in terms of accurately measuring and predicting what the surge will do in this system. And so this is still too coarse to completely resolve small inlet features. So while this model did an excellent job on a regional scale, when you zoomed into small systems like Katama, you had problems. And just to highlight what that looks like, if we compare the AdCirc resolution on NACS to the left to the Katama merged mesh on the right, my Katama merged mesh has resolution on the order of 10 meters in order to capture the flood and ebb shoals. And in particularly for the NACS study, Katama Inlet was closed. And so this treated this system as a hard boundary down to the south. And so similarly, we had to take into account the fact that waves were going to be refracted around, especially the ebb shoal off the southern part of Katama Inlet and relict ebb shoals scattered throughout along the coast. We reduced the resolution also again from 200 meters in the large grid indicated by the SMA grid here. This was the Southern Massachusetts NACS grid. And we created a much smaller but much higher resolution 10-meter grid inside and nested these 2. The SMA grid was used to drive the spectra for the Katama grid, but they used again the same wind forcing, different bathymetry. And so this SMA grid, which is again the NACS grid, it shows this much coarser, sort of very crude geometry. Whereas with the Katama resolution, you can really see especially the flood shoals and channels, as well as the relict ebb shoals off the southern coast of the South Beach here. So bringing you back to the 5 points within the Katama system that I was measuring, and the 6th point out to the south, we can look at just 3 of these points and try to assess how well did my storm surge propagate through the system compared to observations. And to do that at these 3 points, station 1 is again at the top here, station 4 in the bay is the middle, and station 5 is down to the south. And these are all plots of water elevation versus day in August, again reminding you that the storm hit on August 28th. And the first part I'd like to talk about were the days leading up to the storm. And here, just to draw your attention, black and the shaded gray around it are the observations with their relative error. The model outputs for the larger regional NACS grid are in blue. We had the ability to run an AdCirc only with finer resolution, as well as a coupled grid where it's using the high resolution, but with waves as well. And so during this pre-Irene run-up time, for especially in the northern inlet and in the bay, all the models behaved very comparably. The error was undistinguishable between any of the model runs. Down towards station 5, however, is where you see a large difference because, again, the inlet did not exist in the NACS, which is the blue curve indicated very differently from the remaining three. But that if you were to look at wave effects there, you really couldn't see any difference here. This is in contrast to the days leading up to Irene and to Irene itself, where I again draw your attention to the models that try and match the black, which is the observed. And you'll note that down towards the south, both the high resolution and the high resolution with waves do much better than the NACS do, but that inside the bay, that the higher resolution plus waves did a much better job. In addition, we can see how this storm surge progresses through the system, where I show down to the south the time of arrival of the surge at the southern inlet. And you can see to the north that this transpires on the order of an hour by the north. And again, I remind you that this system is small. It is 7 kilometers north to south. And again, because we have the ability to look at spatial variations with this from using model results, here I show you a water elevation difference, where this is the model looking at waves and circulation, i.e. the sea storm model, subtracted just the high resolution circulation alone. What this tells me is these are the wave effects that are residual within this small bay. And so positive here is indicated by red, and in this particular case in the bay indicated on the order of 25 centimeters, suggests that there actually was an increase in surge level at the peak surge event on the order of 25 centimeters inside this small little bay, just because we're including wave forcing as opposed to not. Same resolution on both grids, just the only difference is including the waves versus not. Similarly, I can look at the circulation and the velocities and look at two different features. The red circles indicate the circulation in the northern inlet, which shows no circulation when the inlet is closed during the NACS study, and a little slight northern migration during the Katama sea storm. You also see this coastal jet with the Katama sea storm, and it really shows also this migration towards the north and overtopping event. And I draw your attention back to that satellite picture, which I showed you before. And so to conclude, coupling ST wave and ADCIRC was effective at modeling storm surge at high resolution in an inlet system. During the peak surge, the Katama sea storm model improved on the NACS low bias by over 20%. And resolving low-lying beaches to allow overtopping and accurately representing tidal inlets and the very complex bathymetry that follows them really improved the overall accuracy of the model, both on a temporal and spatial component. And also, interestingly, contrary to prior research where Katama Bay did not show any setup owing to waves, there was actually significant wave setup during the peak storm event. And so with that, I'll thank you and take any questions via email. Thanks.